In this part of video lecture, we will discuss about Clausius Clapeyron equations in thermodynamics. Clausius Clapeyron equation is very important for different type of a single component or multi-component system where the pressure, temperature, and entropy and volume are related. From the thermodynamical equations or from Maxwell equations, we can so easily prove that del P del T at constant V is equals to del S del V at constant T. Now this means that change in pressure per unit change in temperature at constant volume should be equal to the change in entropy per unit change in volume at constant temperature. In order to realize this equation, let's think about we have a closed system that has a volume V and which consists some gas molecules. Now, if we change the temperature of this system, keeping the volume constant, the pressure will increase. Now, from this equation states that the same scenario, if we maintain a system at constant temperature, that means an isothermal process where the volume change will be connected with the entropy. That means if we change the volume, if we increase the volume, the entropy will increase. Now consider a closed system where a liquid and a gas is in equilibrium and it consists of a single component, let's say water molecule. So we have a water molecule that is in dynamical equilibrium between liquid state and vapor, with vapor, the gaseous state. This equation is valid for multi-component system, but for the sake of simplicity, let's consider a system that consists of a single component, in this case water, and that is in a dynamical equilibrium between liquid and gaseous state. That means water and vapor. In such case, the vapor pressure in this system is basically independent of the volume of the system but depends on the temperature. So we can say that del P del T at constant V can be applied in over here. Now consider 1 mole of liquid is vaporized isothermally and reversibly at a fixed temperature T. So, in order to maintain the equilibrium between liquid and gas, now consider 1 mole of liquid is vaporized isothermally and reversibly at a fixed temperature T in this system, so that the liquid vapor remains in an equilibrium. The increase in heat content for this dynamical equilibrium is delta H, then the entropy change should be del H by T. Now we can say that if the volume change due to phase transition from liquid to gas, it is delta V, then del S del V should be constant because it's an isothermal process. So del S del V at constant T is applied over here. From the above equation, we can say del P del T at constant V should be equal to del H divided by T into delta V, where delta H is basically the latent heat, or we can say this is the phase transition heat content. This was first introduced by Clapeyron 1834 and extended by Clausius 1850, and this equation is known as Clausius Clapeyron equation, the famous Clausius Clapeyron equation. Now let's see this phenomena in terms of component. So we know from the concept of free energy and other spontaneous processes, we know that if we have a system that is the same system, liquid and gas, and they are in dynamical equilibrium, then from the concept of free energy we can say that chemical potential of liquid state should be equal to the chemical potential of the gaseous state. So that means the chemical potential of these two phases should be same. Now for small change in liquid state and in gaseous state, we can say that del alpha mu prime plus d mu alpha equals to de mu beta. For small changes in alpha and beta, we can say that mu alpha prime plus d mu alpha equals to mu beta prime plus d mu beta. So d mu alpha and d mu beta are the changes in component for liquid and gaseous states. And if we express this from the expression of free energy, we can write down that this equation where del mu del alpha dt, this is basically the temperature coefficient, the change in chemical potential per unit change in temperature at constant pressure, and this is change in chemical potential per unit change in pressure at a constant temperature, and same for the gaseous component. Now we can show from this expression that del mu del T at constant pressure is nothing but entropy of that component, and del mu del P at constant temperature is nothing but the volume of that component, volume change of that component. So this is molar entropy change, this is molar volume change. So if we replace this one, we can write down this equation directly from this equation. Now this is very easy and you can solve it by yourself. Take it as an homework. Now if we rearrange this equation from left to right, we can write it down like this. So what does it mean? The volume change, molar change in molar volume multiplied by change in pressure is equal to the change in molar entropy multiplied by the change in temperature. If we slightly rearrange this one, we can easily write it down. Del V del T at constant T is nothing but del S del V. Now what is del S? Del S is nothing but del H divided by T. What is del H? This is the heat content, molar heat content of alpha component minus molar heat content of beta component, which is nothing but the change in molar heat content for the phase transition, and this is nothing but latent heat. So if we just by substituting, we can say that del P del T is nothing but L divided by T del V, which is the Clausius Clapeyron equation, where delta V is molar volume change. Now, in order to solve this partial differential equation, let's consider a 1 mole of ideal gas, and that ideal gas behaves PV equals to nRT, follows PV equals to nRT equation. So if we rearrange that dP dt from this previous equation, we can show that dP by P is equals to L by R dt by t square. And if we solve it for two different cases like component 1 and component 2, we can say that the logarithmic relation between pressure and temperature, where delta H is the phase transition temperature. I hope this is understandable. If you have any questions, just let me know. Thank you so much.